yeah, around in 2000. Yeah, so I was working in G for 7 8 years. That during that period, I also worked on solving some of these design issues for this fan blade. So so let's talk about one of the design issue that's called morphing. Okay, so today we are going to talk about the morphing. Okay, so it will involve some of the smart material also. So what is this issue basically morphing? Okay, so as you can see the shape of the blade here, it is not flat. Okay, it is curved. So let me show you here. Yeah, if you look at the blade here, so the left side edge is called the leading edge. Okay, and the right side edge is called as the trailing edge. Okay, and approximate height of this blade is more than 1 meter. Okay, length of the blade or height you can say 1 meter, and the width is approximately half meter. And at the leading edge you can see some metal cap. Okay, this is to protect the blade for burst strike event. Okay, put some metal cap. Okay, but the remaining all structure is made of carbon composite. Okay, so basically what happens is if you look at the current shape of the blade, it's all not straight. Okay, along the length also it is kind of wavy. Along the width also it's kind of curved, so it's not straight. Okay, but what happens is there are different stages of the flying of aircraft. So when aircraft is on the ground, then it starts flying. Okay, so there are different stages like cruise and climb and descent, like this. Different stages of aircraft. When it's climbing, then it reaches certain height, then it cruises, then again when it wants to come down, then it is again having descent. So these are the different stages of aircraft. Okay, so during those different stages, the same blade is being used and the shape is also same. So if you look at the birds, okay, so if you watch carefully the birds, the wings of the bird, okay, so when they are cruising, the wing shape is somewhat typical wing shape is there, which is flat. They don't move it too much. But when they want to change the direction or they want to descend or they want to climb the birds, the directions of these wings, okay, the bird wings, it changes. The shape of the bird wing changes. Okay, so when they want to go down, they will slightly change the shape of the wings. When they want to climb, they can slightly change the shape of the wings. And similarly, when they want to cruise, it's something different. So they can change the shape of their wings at their own, control. Okay. So here, actually, this blade is a fixed shape. So we are not able to change the shape of the blade over different missions of the aircraft, whether it's a climb or descent or cruise. So can we come up with some technology that which will enable this change of this blade shape? That's what this issue was about. Okay, so depending upon the situation where the aircraft is, whether it's on ground running, or it's climbing, or it's at the cruise, or maybe it's having descent. So at those different stages of aircraft, can we have some technology so that we can change the shape of the blade? This is all morphing is about. So let's talk more about morphing. Okay, so what is morphing? The simple definition is this ability of this blade to. I'm talking about morphing in terms of the fan blade. Okay, there could be a different meaning of morphing for different technologies and different applications. But here, as far as the fan blade is concerned, this is the definition that we want to tell. That is ability of the blade to change its shape time to time depending upon the requirements, like wings of the bird. Okay, and if that is made possible, if this requirement is somehow made possible, what it can do? It can yield into 0.2% specific fuel consumption benefit, which is, the number, if you look at it, 0.2% is very small here. Just look at the number. But in terms of the aviation industry, it is used. In terms of the aviation industry, this achievement could be used. Okay. So there are many possible ways were suggested, and we brainstorm and we came up with different ideas what we can do. So of course, most of the ideas went to the active morphing. So active morphing, of course, active morphing is getting very popular right nowadays, and is basically like using some kind of forced activation. Okay, to force the blades and structures to change the shape. okay, whenever required. And the examples are shape memory alloys, piezoelectric ceramics, electric and electronic actuators, like this kind of different technologies are there. Okay. But basically, yeah, I mean, all these ideas are successful and they're implemented for different applications, not for the fan blade. Okay. But fan blade is a very critical component inside the aircraft engine. And to play with this integrity of the fan blade structure by embedding some kind of active morphing technologies will be very dangerous. Okay, so so we say that okay, active morphing is a very problematic thing. It cannot be implemented into this fan blade because it's very critical component. And when you manufacture the fan blade and then basically you implement it, anything that you want to fiddle with, anything you want to change in the fan blade will be very critical. And even small error, small crack, a small error can lead to a destruction. Okay. So if you have heard about wind blades, okay, wind blades are different technology. So wind turbine blades, okay. If you look at the wind turbine blades, there are many active morphing technologies that are already introduced in wind blades, where they can change the shape of those winglets or wings or some part of that wind turbine blades. You can actually implement all those force activation, and you can make the wings move in desired shape. So because why it was done in wind turbine blades? Because the wind turbine blades are open and there's no engine there to damage the engine or something. So wind turbine blades are open in the air, and even if something happens, we can stop the wind turbine blade and go there and check and what happened and repair and come back. That is not possible at all in aircraft engine. Aircraft engine, if something goes wrong, it's very dangerous. You can't do anything about it. Okay. So then it was concluded that active morphing cannot be used as it is, uh, because it is a very critical component. Then what we can do? Can we come up with some other thing? Then we have decided to try this passive morphing. So what is passive morphing? Okay. So basically this blade, composite blade, is made of laminates, okay, layer by layer structure. And basically what we do is we buy this carbon fiber epoxy prepegs, and we hand lay up in the mold shape, and then we cure it, and that's how it is made. Cure it using autoclave. That's how it is made. So generally, this blade layups is always symmetric to have a better integrity of the blade, okay, and to avoid warping and twisting. But uh, yeah, so if we can play with those plies, and instead of symmetric layup, if we can come up with unsymmetric layup, then can we generate some kind of morphing ability in the blade? This was the project was all about. Okay. So if we use some unsymmetric plies to make some composite plate and then cure it, it warps at least under load. Okay. I mean, if you take a simple plate and put some unsymmetric plies, and later on you cure it, and then later on if it is used and some load is applied, it can warp or twist. So this is the concept actually. So what we were trying to do is, can we purposefully use the unsymmetric plies, okay, to create some kind of warp and twist, basically, which can be used as a basically morphing, okay, and that will give the efficiency benefit. But at the same time, we should not lose the structural integrity of the fan blade. So this is what our project was about. So can we use this phenomena in a reverse way for the purpose of morphing? Uh, Sorry, just a minute. Yeah, so can we adaptively morph? Adaptively morph means whenever we require, the blade should morph. Adaptively morph the blade arrow shape throughout the takeoff, climb, cruise, and descent missions, which will increase the SFC. This was the main target. Okay? So let's see how we did it or not. Okay. So to come up with this morphing, so how do you decide how much morphing the blade is doing, or how do you decide how much basically, what is the measure of morphing? Okay, so this is what it shows. Like, let me show you if I can access to annotation here. Yeah. So basically, as you can see, yeah, Actually, the blade shape is not flat. If you look at the blade from the top, okay, the blade may look like this shape, and this is the blade look like this, like this. Okay, this is a horizontal line. With respect to horizontal line, maybe the blade is looking like this. Okay, so morphing means what basically? So maybe this is the leading edge, and this is trailing edge. Okay, and okay, so this is basically the original angle of the blade. Okay, and morphing means suppose you want to move this blade, this cross section of the blade uh, into a desired kind of shape. So maybe that's like moving on this side or moving on this side. Similarly, the trailing edge moving on this side or moving on this side is possible. Okay, so basically if you move on this side, the blade will become like this, or if you move on this side, the blade will become like this. Okay, so basically, so there are two angles here. One angle is the leading edge part making with the horizontal. Okay, other angle is the trailing edge part making with the horizontal. Okay, like this. There are two angles. Okay, so one could be theta one, other could be theta two. And the difference between these two angles, theta one, basically. So what I'm saying is the change here is theta one, change from the original shape to the new shape. And here also change from the original shape to the new shape is theta 2. Okay, so this change in shape from the leading edge side, change in shape from the trailing edge side, the difference is 2 theta, that is called as the camber. So camber is the basically is the measure of morphing here. It's called camber. Okay, so let me show you. So yeah, so this is what we use, and we call it a camber. This is the difference between the change of shape of leading edge, trailing edge, and again taking the difference. That's called camber angle. Okay. Camber is just a name for that angle. Okay. So, so for our blade, our composite fan blade, which is being used at the front of the aircraft engine, so leading edge we don't want to move, because if you remember, there is a metal cap on the leading edge. So leading edge generally we don't want to move leading edge. Okay, so basically then we are left with the trailing edge. Okay, then trailing edge shape can be changed. Okay, so it can be moved on the this side or that side like this. Trailing edge shape can be changed. So basically, it is just a change of the trailing edge, change of shape of trailing edge, and that angle is theta. So basically, that angle will be our camber measure, okay, measure of camber. So, so remember our constants that we cannot change the shape of leading edge, but we can change the shape of the trailing edge. So trailing edge side is only available for changing the shape of the blade. So how do you do it? So let's see. Yeah, so basically, where is the force coming from for this change in shape? Okay, so that force we're going to talk about. Okay, so this is a blade. Okay, and blade is rotating at certain RPM. Okay, so this RPM changes depending upon the stage that aircraft is in. So the aircraft is running on the ground, then RPM may be different. The revolutions of that fan that could be different. If the aircraft is climbing, the RPM could be different. If aircraft is at cruise, the RPM could be different. And if aircraft is descending, then the RPM could be different. So depending upon the difference of these RPMs, okay, the force, basically, what is this force coming from? In the this fan blade is rotating at, let's say, 3000 RPM. Okay, due to that, there's a centrifugal force, inbuilt centrifugal force coming into the blade. Okay, due to this high speed of rotation, 3000 RPM. So that centrifugal force, if you look at the blade, blade is attached at the bottom here. This bottom part is fixed in the hub there. Okay, so and the blade is rotating. Okay, so as you can see, the centrifugal force will be highest at this point root of the blade, and as you go towards the tip of the blade, this is called a root of the blade, and this is called the tip of the blade. So as you go from the root of the blade to the tip of the blade, okay, the centrifugal force changes. This is what is showing graph here. The centrifugal force in x direction. X direction means this vertical direction here. Centrifugal force in x direction, it changes from like this at cruise and at other stages also. cruise or max climb, it changes like this. At cruise also, you can see as you move from the root uh, to the tip, the centrifugal force changes, and also for climb condition also, centrifugal force is different, but it changes like this. Okay, and as you can see, there's a difference between this centrifugal force from max climb to the cruise. So this difference in this centrifugal force, can we use to change the shape of the blade? This is what is the target here. Okay, because there is a different centrifugal force at mass climb and different centrifugal force at cruise. So at these two stages, we can activate that force, and somehow you can bring up the change in shape. Okay. So how do you do that? So let's see that. Okay. So of course, as I told you yesterday, again, the technology for the blade is very complicated. So if you look at the blade, so if you want to play with the blade, whether it's a real blade or it's even the full model blade in analysis, it is going to be very, very complicated. So of course, we have gone back to our usual procedure that we start with some panel or coupon. Okay. So here, of course, we decided that we'll start with some panel, okay, composite panel. And we thought that this composite panel resembles the trailing edge portion here. If you look at the blade, this trailing edge portion looks like the rectangular panel. Okay, so we decided that we'll take the exact layup that is there in this rectangular shape area, which is near to the trailing edge, and we'll build those layups inside this simplified flat panel. Okay, and the boundary connection, of course, symmetric boundary connection will apply here because this is part of the blade. So the left edge will have symmetric boundary connection. The right edge here will have symmetric boundary connection, and X direction load is centrifugal load coming from this rotation of this blade. Okay. This is what the panel level idealization for simulation purpose, and load is of course RPM loading, that X direction loading. Okay. So this is what we try to play with, and let's see. Okay. So how do you play with this unsymmetric layers? Okay. Okay. Let's talk about this. Yeah. So as I have talked about earlier, so if we forcefully, build a layer which is unsymmetric. Now you must be knowing what is symmetric, unsymmetric layers in composite. Okay. I assume that you know symmetric layer, what symmetric layer means and what asymmetric layer means. Okay. So if you have a neutral axis, so below the neutral axis and above the neutral axis, the layers should be same. So symmetric layers. Okay. So symmetric layer and unsymmetric layer. So if we forcefully build unsymmetric layer in the composite, okay, so it creates some kind of warping, twisting in the part when it is subjected to some loading. So how do you know that? What is the theory behind it? The theory behind it is if you look at the ABD matrix. Okay, there is this ABD matrix for stiffness matrix for all the laminates. I mean, I don't know if you have studied the fiber reinforced composite course. There you'll be taught this what is the meaning of this stiffness matrices for ABD. Okay, so there is a direct stiffness matrix part is there, and there is a coupling parts is there. If you look at this part, left bottom and the right top. Okay, this part of the matrix is generally this coupling matrix. So it couples the basically any sort of bending and twisting is responsible, okay, for this coefficients here. This coefficient decide how much bending twisting is there going to happen. So if you have symmetric layup and you have a simplified tension load or something, then this left bottom and right bottom matrix will be zero. Okay, there will be no bending twisting. If you have a simple composite plate and you are pulling it under tension, there is no bending, twisting, nothing. It's very simple for symmetric composite. So this left bottom and right bottom matrices components will be zero. But here we are forcefully introducing this some kind of twisting, bending, and because of that, these components will be fully occupied. All these components will have some value there. The left bottom and right bottom, right top. components. Okay, load is of course nx only, other components are 0. This is the inverse stiffness matrix. So we have to play with this matrix, and we have to see that how can we maximize this B12 and B16 coefficient so that we'll have more bending and twisting. Okay, so that was the goal of optimization. Okay, so optimizing this coupling coefficients. So we wrote some code in MATLAB. Okay, and so algorithm was written, and so we kind of give the input properties, and we give some initial ply orientations, and then it calculates the stiffness matrix, and it also calculates this ability matrices, and then our algorithm kicks in. Our algorithm says B12 and B16 has to be maximized by changing the layer orientations. Okay, and then it keeps on iterating for many iterations. Okay, and tries to maximize this B12 and B16. Okay, and finally after a lot of iterations, it will throw away, it will spit out the optimized layup for maximum B12 and B16. This is what the algorithm is, just written in MATLAB. Okay, so let's see. So yeah, this is what it shows like. So okay, every dot means one single iteration. Okay. For a typical load and simple that layup you have. Okay, so you keep on doing these iterations for ability matrices, and for maximizing B12 and B16. And as you can see, every dot represents one iteration. So you can see the value of B16 and B12. If you plot it like this, the right top rectangle or right top quarter, that is the region of interest, because there's a positive value of B12 and positive value of B16. So both of them are positive there, and both of them have high value there. So that is the region of interest where we want B12 also maximum and B16 also maximum, so that this unsymmetric layup can create this morphing. Okay, so this was done in MATLAB. It was done for a simple 6-ply laminate, but this is just one example. But of course, we have tried for many different layups. Okay, that will show you. Okay, so then once you come up with this thing, then this code will spit out some optimized layup for 6-ply laminate. Then how do you test it? So we took that 6-ply optimized layup, which is obtained from this iteration of MATLAB code. Some layup we got. This layup we again use that simplified panel, and we implemented those layups here. Okay, and we applied centrifugal force and saw that it is going to warp and twist. Outer plane deflection due to this in plane and bending coupling, because the matrices, okay, for this particular layup, the inverse matrix, stiffness matrix, you see B12 and B16 are the highest. So you can see there's a maximum amount of bending and twisting is happening there. The trial on this optimized layup is done on panel level to check how much twisting and bending under the axial load. So you can see it's showing. So we'll show you the result. I mean, what different panels are giving what kind of results. So let's see. Yeah, so if you look at this results here, okay, so these are the different layups that that our MATLAB code has said that this layers looks promising, and coupling coefficients were optimized. As you can see, some cases B12 went up, B16 went down, or some cases B12 also went up, B16 went up, and B11 went down. Like all these different combinations that we tried for optimizing these coupling coefficients. And you can see the different layups, and for the NX loading of 107 pound per inch, 141, because these are two different loadings we tried, and then found out the camber change. So you remember camber change? Again, the camber change will be the change in the angle from one shape to other shape. So for example, for NX equal to 107 pound load, we'll find one angle theta 1. For NX equal to 1 for 1, we'll again run the case, and we'll analyze the results and find the angle theta 2. Then delta theta is the theta 1 minus theta 2. That is the camber measure. Okay. So as you can see, for different cases here, you get different camber. So ranging from like 1.08 degree to 0.5 degree, 2 degree, 1.99 degree, 3.89 degree, 2.56 degree, 4 degree like that. Okay. So for some optimized layers, panel level camber change is computed and going up to 4 degrees, which is encouraging. Because encouraging in the sense that I don't know whether I mentioned earlier that for getting that 0.2% SFC benefit, okay, we have to have at least 8 to 10 degree camber. Okay, that was the target. Okay, but here is going to show up to 4 degree, and we thought that that is encouraging. So maybe we thought that this is only for 6-ply layup. If we use more plies, and we can see if we can get more than 4 degrees. That's what the expectation was. Okay. Then we also tried this panel size effect, the width and length of panel, because we, initially we assume certain width and length of the panel from that trailing edge region. So of course, if we can play with that width and length, what is going to happen is through this camber angle. Okay, so as you can see, if you increase the length of the panel, of course, camber increases, camber angle increases up to certain level, and then it drops. Similarly, if you try to increase the width of the panel, then camber angle increases and then drops. So combination of this also you can see somewhere you can get, but later on it plateaus, it flattens out. Okay, so these effects are studied for panel size effect because that was also important because we assume that it is just initially we assume some dimensions that is part of this blade trailing edge area. Also, there was a thickness effect. Thickness effect was very important because the panel that we the trial panel that we played around was only 6-ply thick. Okay, in reality the blade is very thick. In reality the blade may have like maybe 100 layers inside it. Okay, certainly more than 80 layers. So the blade is thick actually compared to this panel. So that's what we decided we should study the thickness effect. And as you can see for the panel level, we try to find this based on the thickness. If you increase the thickness, what happens? So this B12 plus B16, which is also indirectly a measure of our morphing. B12 and B16 is the coupling coefficients. So maximum coupling coefficient, combination of this coupling coefficient for this thickness is this. And as you increase the thickness of the panel, that means you increase the number of layers in the panel. As you can see, the coupling coefficients go down. Okay, even for the maximum case that you found, it goes down. Okay, similarly, log scale also shows it's going down. Okay, so this thickness effect was very important for us because although we are trying the panels for 6 plies thick only, that's why it was showing very promising result. Now we understood that if we go to the real thickness of blade, so we are worried that how much morphing camber is going to show. So let's see. Yeah, so this was the laminate stacking that was used for the thickness effect. As you can see, we try to vary the number of plies and change the thickness like this. And then we saw what happens to B12 and B16. That's what's shown here. These cases were done for panel. Okay. Then based on the thickness variation, what we did is just approximately we try to calculate this. This is the section of the blade actually. If you look at the section of the blade, as you can see, this is the tip of the blade at let's say a trailing edge. And as you go away from the trailing edge, as you can see, this thickness is increasing. Thickness is increasing. At the tip also, thickness is not zero. So there is at the tip also there is certain thickness and certain number of plies. And as you go away from the trailing edge tip, number of layers increases. Okay. So based on that earlier thickness calculations and the camber, we manually try to calculate this based on the thickness variation. That what could be the camber? What could be camber over the whole blade? Okay. So we try to find the change in angle, and then finally found that it could give us maybe 0.85 degree angle change. That is camber change. Okay, because camber is inversely proportional to thickness, so approximate entitlement for the whole blade was computed from for the blade from mid thickness to tip. Okay. So this was just, as you can see, the number of plies are increasing step by step, and it could go to 80 plies here. Okay, starting from 14 plies. Okay, so yeah, so doing all this calculation on the panel was okay. It was okay, and panel is showing some encouragement is fine, but the blade thing is totally different, very complicated. So how do you do that in the blade? So we took the actual blade, ANSYS model, and as was discussed earlier, that we chose that trailing edge region there. Okay, and trailing edge region we kind of separated. Separated means basically inside the blade only, but treated that area separately, and we assigned the local coordinate system there. And because we wanted to incorporate the layout that has come from the MATLAB code. Okay, because if you remember, the MATLAB code is spitting out this optimized layup. So the optimized layup has to be implemented in the desired region. However, the other region of the blade, we have to keep it undisturbed. We have to keep it undisturbed. Only in the desired region, we can implement that optimized layup. So that for that, we created this local coordinate system using ANSYS Capital script and implemented that layout. Okay. Then there also we tried the different size of these panels. First we tried the small region 3 by 8 inch. Then we moved to the larger region 7 by 17. Then we moved to the much larger region 12 by 18. So I'm sorry, this inches units, is coming from this basically American companies like to use this inches unit as compared to Indian companies or British companies, or Europe generally uses this meters, but in America they like to use inches, so that's why it's inches there. But yeah, so basically we try to vary this region, and every time we created a local coordinate system there and incorporated the optimized layout, and then we try to measure the camber, okay, for this actual blade. So these are the results for the actual blade. Okay. So as you can see, the baseline blade, so which doesn't have any kind of unsymmetric layout. Okay. It shows a certain camber change under different loading, cruise and max climb. Okay. And then we try to incorporate these different layups that came up. Okay. As you can see, the all unidirectional or unidirectional with NX load. Then this layup 1, layup 2, layup 3. Like that, there were many optimized layups that we tried. Layup 17, layup 18, layup 20, many. And also the morph region, different morph regions that we tried. 12 by 18 or 3 by 8 morph regions. And then camber angle for cruise, camber angle for max climb, and the difference is camber change. So that's what we tried. And as you can see, all these camber change are very, very small compared to what we saw in the panel, because the panel was very thin, so we could achieve like 4 or 5 degree in the panel. But if you look at the blade, it's showing only like what maximum is 0.34. Yeah, 0.34, something like this. So it's very small maximum. Okay. Then we thought what else we can do. Okay. Then we thought about this density change effect. So if you look at the blade here, if you look at this area here, okay. So suppose let's say this 12 by 18 area, 12 by 18 area, okay. The blade has a certain density. Blade is made of all carbon composite, okay, and it has got a certain density depending upon carbon epoxy composite density. Okay. So what we thought that suppose this selected area here, which we want it to morph. So can we change the density of the selected region here, red region? Can we change by some way? Can we change the density of this region? I mean, how to change the density? There are different lot of options are available, but first initially we just wanted to try whether if we change the density of this region, what is going to happen? Okay, Of course, the ways to change the density, we'll talk later. But if we change the density, then what could be the effect on the morphing? Will it enhance or will it decrease? So basically, the idea here is if we increase the density of this region, maybe this region will become heavy compared to the remaining blade. And when you try to morph, it will morph more because of this overhanging effect. If you remember the overhanging effect, so like compared to the remaining blade, if this density is high, then this high density region will act as a overhanging thing, and under the morphing force, it will morph more. That's what the idea was. So if you look at this blade morphing comparison, there you can actually see where was that? Here, density change effect. So here we try to change the density of few elements here and there in that region, or maybe some rows and some columns of those elements in that region, that red region. Okay, you can see, and uh, the camber for low RPM, camber for high RPM, and the camber change we calculated for all these cases. Okay, so we found that yes, it is helping. Yes, the density change is helping. So if we make that red region somehow heavy, then it is helping, and it is camber can be increased to 1.5 degree, but at the cost of increasing the fan blade weight. Because if you change the density, if you increase the density of that red region, of course, the overall weight of the fan blade will also increase, which is not desired. And also the camber change is how much we are getting, 1.5 degree, which is also not enough. Okay. So we reach to the conclusion. Okay, so thickness plays a bad role here. Thin panels were showing a large camber. However, the thick blade does not show much. Okay, maximum morphing that often using unsymmetrical layup and the density change, that is that morph region density. If you change it, it can get to 1.5 degree only, which is not enough to get maximum efficiency benefit. If somehow we could have reached like 6 to 8% morphing, then maybe all these efforts is worthwhile. Okay, so passive morphing is not going to work for required amount of morphing here. Okay, so then of course active morphing may work, but need to pay attention to safety. And for all these efforts, we filed one patent for this passive morph. Okay, so going ahead, what to do? So we decided, yeah. So of course, going ahead, there was no other option but to go for active morphing. Okay. So what are the different options? Okay. So first, we found that this piezoceramic composite actuator information that we found, and we try to contact the manufacturers and talk with them, and they said that they can provide very thin layers of piezoceramic material, okay, which can be actually embedded into the laminated composite. Okay, so the manufacturer agreed that they will provide us very thin layer of piezoceramic, which will when we hand lay up this carbon fiber epoxy layers prepex, that time only we can incorporate those piezoceramic layers, and that's how we embedded those layers inside the composite laminate. Okay, and the idea is, if you know the piezo, what is the function of piezo, you must be knowing. Okay, so if you change the voltage of the piezo, of course you can create some mechanical stress, of course. Okay, that's the principle of piezo, and vice versa also. Vice versa, if you apply some force to the piezo, it creates the voltage. Okay, vice versa. So by changing the voltage, mechanical force could be applied, enabling the blade to morph. This was the idea. So again, I'm talking about that red region that we saw here. Remember, yeah, here inside this red region only, if we can incorporate some piezoceramic layers, embed some piezoceramic layers inside the laminate layup there, and then try to do this morphing by exciting that thing. But again, the problem was, okay, so if you incorporate the piezoceramic layers there, of course, the wiring has to be done. So there should be some wirings coming from there and going to the root of the blade, and from the root of the blade, it should go to some electrical circuitry where you can actually control the activation, deactivation of these layers. So that was the problem. So where are we? Yeah. So initially what we tried is we try to do some ANSYS simulations by incorporating those layers in the layer. Properties were provided by the manufacturer by how much voltage change, how much stress is applied. So of course that electrical piezo effect is difficult to implement in ANSYS. So what we did is we came up with equivalent this thermal effect, equivalent thermal effect compared to this voltage effect, voltage versus strain, that we converted into temperature versus strain, and then we incorporated into ANSYS equivalent thing, and then we try to run and see whether blade is giving the morphing. Okay, so so we found that it was promising. Basically, this incorporating this piezoceramic layers in the laminate was using the analysis we found it was promising, and it was going to almost 6 to 7 degrees morphing. Okay. However, the question remains: embedding a foreign object into a solid and integral composite blade is a dangerous thing. Of course, you know, anything which is very small thing, even if it is very small and you embed into integral composite blade, it can lead to delamination and all those kind of things. So may lead to cracks and delamination, which may lead to failure. So that's very dangerous. So the question always remains: how do you justify this safety factor? So idea simply cannot be implemented. Sorry, there's a typo there. Implemented at this current stage. So the company is still working on it and still trying to figure out how to implement this into handle, because we need the technology to be evolved. Piezo technology or some other replacement technology need to be evolved. And again, based on their idea, we file a patent on that. Yes, patent. Yeah. So where are we? Okay. So yeah, this is just an example of some literature survey. We did not do this, but just for your understanding. So if we use the piezo-based patches or piezo-based layers like this is the example of piezo-based patches which are put on some small blade here. You can see some small blade is manufactured in the lab, and the piezo patches are kept on that. And as you can see, if the voltage difference is varied from plus 1500 to minus 1500, you can see the change in shape. Similarly, at the bottom also, if you see the voltage level from 1500 to minus 1500, you can see the change of shape. Okay, so mechanical stress could be applied by changing the voltage strategically on strategically located patches or foils can enable the wing morphing. Okay, so of course this can be used for some simple applications, but not for the fan blade in aircraft engine, which is very tough. Okay. Then of course, as you can see, these are the things available in the market. Piezo patches, you can see the piezo patches here. Here also piezo patches and piezo ceramic layers, and this kind of piezo patches also available. So you can put like a bunch of piezo patches together on the blade like this, or like this piezo patches. These are all different things. Piezo based. What do you call it? Smart materials. This is actually the smart material. So all the piezo based smart materials are available, which can be used to mark the wings or blades like this. Also, shape memory alloys. If you have heard about shape memory alloys, shape memory alloys are very popular nowadays. And basically, what does it do? Shape memory alloy. Okay, so if you heat them up, basically they can change the shape. Shape means why they call it shape memory alloy, because it retains the memory of the previous shape. Okay, let's say you have a shape memory alloy and you are applying force to it, and it has deformed into certain shape. Okay, and then if you hit them up, they will try to go back to their original previous shape. Okay, they retain the memory of the shape. That's why they call as shape memory alloy. So they can change the shape on application of it. They can be embedded easily into any structure, And as you can see the examples here, the unmanned aerial vehicles is very popular application, unmanned aerial vehicles, where they can change this winglet shape. This is called as the winglet, the right end and left end, the tip of the wings basically, they are called winglets. So the winglets can be morphed. Morph means actuated by changing this, just apply a small amount of heat and you can activate and deactivate this shape memory alloy actuators, and you can change the shape of this wings basically. Okay, so this is what is getting very popular right now, shape memory alloys. Okay. Okay, I think that this is what I have today. Any questions?
Request the participants to kindly raise your hand, and I have given you the option of unmuting yourself also. You can unmute and you can ask a question.
Yes.
Any questions from the participants? You can unmute yourself now. Vijay Kumar sir, are you talking?
Yes, any question, please?
So presuming there are no questions from the participants, thank you very much, Prakash sir, on behalf of the team MLR IT.
Thank you. Yeah, my contact is given here. If anybody has any questions, you can always email me.
The session is also aired on YouTube. You can watch the live or the session afterwards if you have in case missed the beginning.
Okay. Thank you, madam. Thank you for the opportunity, and I appreciate.
Thank you very much, sir, for your time, 2 days of your time and sharing your knowledge with us. You're really having a versatile, we are very happy to have you here, actually 26 plus
Thank you,
years
madam.
and all. So on
you.
behalf of Gupta sir also, I would like to convey my regards.
Thank
And
you,
I have my associates here, Sai Prakash sir, Uday Ranjan sir, Deepika ma'am, Nagraj sir, who are all in the meeting right now. So on
okay.
behalf of everyone, I'm conveying you a very heartfelt thanks.
Okay, thank you. Thank you, madam.
Thank you, sir. And a
Okay,
big thank you to the participants for consistent support you have been given for the past 5 days.
Okay. All right. Thank you, madam. Then I will log out.
Yes, sir. Thank you so much, sir.
Okay.
Gupta sir would be calling you.
Okay. All right. Thank you.